All right, y'all, we're going to talk real quick about optimization problems, maximizing, minimizing things. Okay, a lot of times we're looking at boxes with no lids or boxes with lids or sum of two numbers or something like that. So, first of all, if it's anything like a box or whatever, you always want to draw the figure. You always want to do that. And then write a first equation. Okay, a box with no lid is made from 48 centimeters squared of material. So what is that if you think about that? Well, that's the material, that's the surface area. It also kind of helps that it says centimeters squared. I know that's surface area. The box must have a square base. So you know it's normally like length times width times height. Well, if I have a square base, I'm going to go ahead and call that x and then that x because they're going to be the same. And then I have my height, which I can then call like y or something. I mean, you can leave it as h, but right? Find the dimensions that will produce a maximum volume. So I'm trying to go volume max. Okay? Now I have two different equations I'm going to be working with. I have a volume equation and I have a surface area equation. All right? So let's go ahead and set these both up in terms of x and y. Because this is x, y. Okay, so my volume equation is just going to be x times y. That's my volume. My surface area, all right, the base of this box is going to be x squared. Each side is going to be xy, and there's 4 of them, right? There's 4 sides. So there's 4 of those. And there's no top. Now, if there was a top, we would put it here, but there's no top. Okay? And I know that that equals 48. So look, I have these two equations. I have this equation, I have this equation. All right? Now, it's like we have two equations with two variables, okay? And so the easiest way to do this is, and it kind of says over here, write a primary equation, isolate whatever is to be maximized or minimized, rewrite it with only one variable on each side, and then write a secondary equation. Okay, it's like this. I want to solve for y, all right? So when I do that, I get 48 minus x squared. So I end up getting y equals 48 minus x squared over 4x. Okay? Now I'm going to take this and put it in right here for y. So now my volume is x squared and then 48 minus x squared over 4x. All right, and this is my volume equation that I'm going to work with. Okay, guys, so real quick, all right, so we have our, volume equation, that's our primary equation. We have our secondary equation. Okay, we got to rewrite it with only one variable. We did that. Find the domain. We should stop and do that real quick. All right, well, can you see that x can't be 0 because the bottom cannot be 0? Okay. The other thing is, you guys, we can't have a 0 side. So not only can x not be 0, it has to be bigger than 0 because we can't have a negative side. All right? All right, that also means if I look in here at this 48 minus x squared, right? Do you guys agree with me that that has to be a positive number? Because if it's a negative number, I get a negative volume, and it can't be that either. So x cannot be, well, let's see if I can solve this here real quick. X has to be less than the square root of 48. Or else that would give me a negative volume. So my domain looks like this. Let's put it like this. 0 is less than x is less than the square root of 48. Okay, this is my domain right here. Because again, if it's bigger than the square root of 48, it's going to give me a negative volume, and we don't want that. All right. Let's simplify this a little bit. If I cancel out one of these x's, distribute that through, so I've got 48x minus x to the third over 4. And maybe I'd rather write this as, I'm going to go over here. 48 over 4 is 12x minus 1/4 x to the third. Okay, that's my volume equation. Now, how do we maximize or minimize anything? By using a derivative. The derivative will find us maxes and relative maxes and mins because those are critical points, right? Okay, so if I take this and I go ahead and find the derivative of that, which is going to be 12 minus, if the 3 comes down, 3/4 x squared, okay? Bring that over. You guys, dividing by 3/4 is the same as multiplying by 4/3. So I end up getting x squared equals, 3 goes into 12 4 times 16. So x equals plus or minus 4, but of course I only want to use the positive 4. Okay, so now let's see if I could write this up. My dimensions are, my box is going to be 4 and what is it, centimeters? By 4 centimeters by 4 by 4 by, now how do we decide what the last part is? Well, I got to plug this in somewhere and solve for y, okay? And, I mean, look, I could plug it into, let's look at the different places. We could plug it into here. We could plug it into here. Okay, we could plug it into kind of either one of these. I could plug it into, yeah. Let's plug it into this one right here. Okay, 48 minus 4 squared over 4 times 4. Okay, 18, so 32 over 16, which equals 2. So this is 4 centimeters by 4 centimeters by 2 centimeters is my box. And then if I'm actually looking for the max volume, now this said find the dimensions that produce a max volume, so I'm actually done right now. But if it did say find the max volume, well, I just plug that in there. And it would be 4 squared times 2, so it'd be 32 centimeters cubed is my max volume. All right. Now it looks like a lot of like algebra, it really is, you guys. There was one calculus step in this entire thing. And that was right there where I took the derivative. Everything else is algebra. Okay? Okay, let's look at this one. All right, the product of two positive numbers is 288. Find the two numbers so that the sum of twice the first plus the second is as small as possible. As small as possible means to minimize. Okay? So let's call the this the sum, and I want to minimize the sum. Okay. Okay. Well, this over here is my secondary equation because it relates x and y and it has an answer there. So I'm going to go ahead and solve for y in terms of x, and then I'm going to take this and plug it in here. Okay. So the sum is 2x plus 288 over x. Now, how do we maximize or minimize anything? With the derivative. So I'm going to take the derivative of this, which gives me 2. And then, okay, let's just go out here for a second and talk about how we do the derivative of 288 over x. If I call that x the negative one, the derivative is negative 288 x to negative 2. So over here, I'll go ahead and make that minus 288 over x squared. Set that equal to 0 and solve it. Okay? Okay, if I bring this over, I can put that over 1 and I could cross multiply. So I get 2x squared equals 288. X squared equals 144. X is plus or minus 12, but it did say two positive numbers, so I need to pick positive 12. All right. So x is positive 12. So now I can go ahead and plug it into this one, I guess. 12 times y equals 288. So that would equal, I believe, y is 24. So the two numbers are 12 and 24. Okay? Now, how do I know that that's a maximum, not a minimum? Really good question. Let's test it. Okay, we didn't do this before, but we can do a sine line graph at 12. And remember, with our sine line graphs, we plug into here. So if I do a number less than 12, like 0. Oh, and on my sine line graph, right, I only go from 0 to square root of 48. Oh, that was the last problem. I'm getting in my head. What is the domain at the very end? Actually, I think we could just keep on going. We'll still see it here. Okay, if I plug in a number like 1 right here, 2 minus 288 is very, very negative. If I plug in a number like 100, 288 over 100 squared is a very small number, and 2 minus that is positive. So because it goes decreasing, increasing, I can prove that that will minimize it specifically. Okay, and there we go. That's the end of 5.4.